analysis and how it can be helpful for our purposes. And finally, we'll take a brief look at model evaluation metrics, and I will also note some things that you should look at when it comes to competitions or business use cases. So yeah, let's get started. First off, what is exploratory data analysis? So let's say you get some random data set. You have no idea what it is. Maybe there is a brief description about the different fields, the different columns that are there in the data set, but beyond that, you don't really have much of an understanding about the data. So then exploratory data analysis is about understanding the data set before modeling. So you need to understand what sort of data there is, what sort of distribution that data is in, what relationships different columns or different fields have with each other, what ranges the data is in. So you can like wrap your head around the data, and whenever you have a question afterwards about how to proceed, you can easily answer that. So you can think of feature engineering steps easily if you understand the data, the relationships between the data, and maybe if you want to visualize the data or prepare a report to show to a business use holder, or in this case, a competition judge. You know what the data is about, you know what the most important things are, you know what are outliers, you know what is common and useless data, and what is extraordinary or important data when you have a good understanding of the data. So as goals of exploratory data analysis, we look at understanding distributions, types of data. So for example, are they numbers? Are they categories? Are they say, encodings or anything in between? Scales. So maybe some data might be in things like meters, something in centimeters, cardinality, etc. And then you want to look at missing values, outliers, how often you find missing values, what sort of outliers, which columns have outliers, and then correlations and patterns in the data. This can be especially useful if you are preparing reports, if you are analyzing trends, or if you are trying to maybe cluster or group together certain sorts of data, or many things. And finally, of course, all of this is very important to generate ideas or hypotheses and guide feature engineering. Feature engineering, while I will not cover explicitly in the session, feature engineering is a very important part when it comes to data modeling, especially when it comes to competitions. You will be judged for how creative, uh, how intuitive, and how much exploring you have done to do the feature engineering. And all of these tools we are going to be looking at today will be important to be able to come up with such things. Um, so again, here are some typical things looked at when it comes to exploratory data analysis. So I will show you a simple notebook here. So for today's session, I'm just going to use Python with sort of Jupyter notebook-like things. But depending on your environment, you might be able to use something like R or Julia. There are plenty of tools. So if you are used to those tools, please use them. But otherwise, if you are a beginner, Python and Jupyter notebooks are a nice place to start. So first off, you can take a look at your data, see some example rows, uh, the different columns there are and what sort of values they take. Then you can look at some things like shapes, null counts, type of data. So for example, here you can see there are integers and the rest are objects, which might be some sort of strings or something more complicated, probably categorical data. And you can see things like how many rows you have, how many columns you have, uh, how many non-null counts. So maybe a lot of these have some value, but some rows in some columns you can see are missing values. And then you can look at summary statistics if there are numerical columns, so things like mean, standard deviation, minimum, maximum. For example, if you have a range of data. Here you can see the age of the people. So generally people, if you take the two distinct quartiles, you can see 25 to 51 age people are constituting probably a majority of data in this. But you have people from 17 to 90 years old. So depending on that, you can get a feel for the data, what kind of people there are, uh, how much they work. So here again, you can see that people typically work 40-hour work weeks, give or take 12 hours, which is probably, so you can also think about like the real world implications of that. For example, maybe this is 40 hours is general work week all around the world, but maybe there are people who do overtime and then there are part-time workers. So maybe good idea here would be to plot the distribution here, see if it has several peaks, which would explain the real world implications of that being part-time, general and overtime workers. So wrapping your head around these statistics can be very helpful. Um, Again, so here you can see missing values. There are three columns with missing values, and this is how much there is. And if you look at our original data, we have roughly 32,000 rows. So maybe in the grand scheme of things, these 2,000 rows are not very important. So maybe we can just get rid of all the rows containing missing values. However, if it's a more significant fraction, maybe that's not something you can do, and you might want to look for um, things like imputing certain missing values. And again, you can see like distributions of missing values, etc. And here, so I've dropped those missing values for simpleness. And here again, you can do some simple plots to understand the different data. So here, for example, you can see how there's distribution. So you can see that the most significant part of people are this. So maybe people who are like 75, 80 years old are not really important for us here. And education levels. So you can have different plots to different visualizations to understand different data. So depending on the type of data, maybe it's numerical, maybe it's categorical, maybe it's some sort of ordinal or some weird sort of data. Depending on that, you can decide on how you want to visualize that and uh, understand the different columns, fields of data that you have. And finally, a very useful thing for, especially for numerical columns, is a heat map where you see how correlated features are. So maybe here you can see education number and capital gain, for example, have some sort of correlation. And so does education number and hours per week, but overall it's a very weak correlation. Uh, So when it comes to models, some models, for example, don't work well with correlated data. So in situations like that, you can look at this and decide to not have that sort of data. Or maybe for visualization purposes, if there are highly correlated data, you can see how other data, those two data with each other in plots. So you can decide what to visualize based on that. So some a lot of visualizations there. So if you think about it, visualizations are a tool we can use for this exploratory data analysis. And so that brings us to the next thing we will cover. So data visualization. Uh, so exploratory data visualization tells us what's going on, but exploratory data analysis tells us what's going on, but data visualization is what actually shows us, right? So you can think of data visualizations as a set of tools for this purpose. So the tools are the different kind of plots or graphs or whatever that you can plot. So if you Google search and look around a bit, especially if you look at some of these plotting libraries, you will see a vast number of different plotting techniques, plotting tools, plotting graph types that you can use. But for this session, I'll quickly introduce you to a basic categorization based on the variables that are there. So you can think of that as univariate visualizations, where you are trying to understand some data related to a single variable, or bivariate visualization, where you are trying to understand data related to two variables, including maybe the relationship between those two variables. And then again, multivariate, similar to bivariate, but multiple. And typically, these are especially useful for numerical data, although some of these there are ways to use it for categorical data, such as bar charts and whatnot. But categorical data, again, there are specific visualization techniques that are useful. So again, why do we want to use data visualization? So obviously, as we talked about earlier, one reason is exploring the data to understand the data, spot trends, identify outliers, missing values, and see maybe class balance, etc. But also, especially important when it comes to feature engineering, to explore feature relationships, like I mentioned earlier. So you can see correlations, interactions between variables. Maybe you can think of a way to aggregate two variables based on the relationship or interactions they have, uh, by plotting the two in a scatter plot and seeing, oh, look here, there might be a pattern that makes sense. Um, so that is another use of data visualization. And then to monitor and debug models, especially if you have a model, maybe you can uh, plot the predictions the model makes and see, maybe in a scatter plot between two major variables, places where the models are underperforming. For example, maybe the model is underperforming for people who are older than 70 years old. So if you plot a scatter plot and see that most of uh, the false predictions are in that area, maybe that's something you can grasp easily from a visualization. And finally, last but not least, actually, this is probably the most important thing, no matter whether you're a data scientist doing your actual job and trying to present something to management, or you're a person doing a competition and you want to present to the judges, to communicate with stakeholders. So you can use data visualization to show the importance of whatever you are doing, whatever your data modeling. For example, you can show, okay, these are the relationships there are, these are the problems there are. You can justify modeling distance, your feature engineering distance, and again, you can present insights based on data visualizations. So it's a very important tool when it comes to communicating and making sure that other people know the importance of your work. So something to keep in mind, especially for the competition, if you have to present or if you have to write a report, make sure you think from the judge or the business users perspective, in addition to technical details, in the business user's perspective, and try to include appropriate visualizations and as well as insights related to those visualizations. Uh, let's take a quick look at something. So again, you can see some different types of visualizations. You have like a basic bar chart. It's more for histogram, and then another bar chart with this way. Bivariate visualizations, a very useful one is is box plots, where you can have multiple blocks box plots for different categories, or maybe I don't remember what exactly these are called, but like bar charts with multiple bars or columns, whatever. Multivariate visualizations. So again, look at, if you have time, go through the code, look at the different libraries I've used. They offer very simple methods to easily make all of these plots, but you can have pair plots, which basically show the distribution of two variables relative to each other. So here you can see these are all the scatter plots of variable A and variable B, and here age means the distribution of age. So it's very helpful visualization. And of course, I think we looked at a heat map earlier, but correlations can be visualized easily using heat maps. Of course, there may be other uses for heat maps so also, but so make sure whenever you have some data that you want to visualize, make sure you think about why you need it and how you want to visualize it, and then search and try to find out the best visualization for that. And categorical visualizations again, and if you are interested, there are some weird visualizations that you might find useful here and there. Next, I'm going to look at a particular technique that's very useful and sorry, give me one second. Yeah, sorry about that. One particular technique that's very useful when it comes to many data modeling things, whether you want to visualize data or whether you want to have more generalized models or remove useless features or even aggregate high dimensional data so that it's easier to deal with or easier to understand. So basically, dimensionality reduction is the process of reducing the number of input features while retaining as much meaningful information as possible. So what does that mean? Let's say, going back to our data set, we have 15 columns. What if we can make three columns by some sort of mathematical formula, reducing those 15 columns, categorical, numerical, into three columns that explain most of the variance in those 15 columns. That way, it's much, for example, it's much easier to plot because 15 columns, actually, there is no way to plot on a graph that you can understand, right? For example, so dimensionality reduction in that sense is about reducing the number of columns, number of features into a very small number of or dimension of features. So essentially what you're doing is you start with a big dimension, 15 features, and go to a small dimension, 2 features, for example. Uh, so I'm going to show you a few methods you can use for dimensionality reduction. Um, the simplest and the best place to start is principal component analysis. But if you want, there are some other methods. So TS in EA is based on like T distributions. It's a statistical method, and UMAP is also another. I think it's an algorithmic method. And finally, variational autoencoders are a deep learning based approach. So we'll take a look again some of these. So these are particularly useful if you want to visualize multidimensional data into using 2 features that explain most of the data. So, and they're also very useful if you want to do things like clustering, for example. So if you are asked to find 3 clusters of data within your data set and try to explain, like, based on that, 3 groupings of maybe people, for example, in this uh, data set, maybe 3 groupings of professionals based on a combination all of this. That's a good application of clustering. So For situations like that, also dimensionality reduction techniques can be very helpful. Um, so I'm not going to go into the math behind PCA. So that can actually be quite complicated. There is some matrices and calculus involved over there. So we just look at how to quickly use PCA. So these standard libraries, you have plenty of methods to use all of these, and using PCA you can calculate principal components. So actually what this will do is this will calculate some number of principal components, and then you can order the so principal components are like new features, and then you can order these in order of how much of the data they explain, and then you pick the top two and you can plot this, and now you have a very good visualization where you can see based on these principal components if your data is well separated, for example. So here you can see that uh, as you go this way, uh, the income category 2 is more prominent. So this explains a good amount of the variance in the data. So in this particular instance, you can see we have we have calculated 10 principal components using our 15 columns. And this explains most of the variance in the data. This explains the next amount. And if you see, uh, all of these explain a considerable amount of variance within the data. So there are other methods, and so this is TSNE. It's particularly useful if you're working with like clustering, and then you have UMAP, and I want to show you also the code of how you could do a variation and autoencoder too. So here you can see that, and here you can see so we've created two latent dimensions, I think here. Yeah. So essentially we've reduced our 15 columns, these 15 columns, into two dimensions over here. And based on those two dimensions, wait, 1 second, how do I annotate? Uh, you can see how there is like a big cluster containing most of the uh, positive uh, positive data points over here. So using these two latent dimensions, you can actually, one, improve the input or prediction models, two, visualize the data, three, try to figure out what sets these apart, and do stuff like that. So again, similar to PCA, it's a very good reduction technique, dimensionality reduction technique. So next, I'm just going to briefly touch on this because I'm not actually going to cover this in detail in the session. So feature engineering. So if you look at our data set, we start with these 15 columns. But maybe there are like things that we can calculate based on these columns that might be good for some models. So maybe we can add a new column, for example, saying, okay, age plus uh, age plus education. So in that case, that would be a very good input that the model would not be able to understand otherwise, because having a high school education only at age 17 could mean a completely different thing from having a high school education only at age 30. So maybe that might be a good input for a certain model. So of course, it isn't necessary for all models. Some models might actually be able to sort of comment those relationships on their own. But that kind of engineering can get rid of useless data, noise. It can add things that you simply uh, did not see earlier. Another good example is if you have names, for example. So maybe you have some names like Mr. John, Mrs. Jane, Miss Diane, whatever. And if that's the only text data you have, you might be able to feature engineer and create a new feature called title. Title being Mr., Mrs., Miss, Doctor, Reverend. And then that can be a new feature that you have. So there are many common techniques such as encoding, scaling, extraction, and like I mentioned, the example I gave, there are some domain-specific methodologies also when you're doing feature engineering. So make sure you use the tools we talked about, exploring the data, data visualization to see the relationships between features, to think of new features, uh, and uh, come up with good features, and also evaluate how good those features are based on, again, visualizations as well as the modeling aspect. Uh, so yeah, I just want to mention that this is a something based both on your technical knowledge, your effort, as well as your creativity. So something you want to think about, because I will not be covering it much in the session. Next, we are going to look at some algorithms. So first, we'll look at some basic algorithms. These are very good starting points for classification and regression tasks. I'm afraid I've forgotten to consider clustering tasks. But again, if you are looking at clustering tasks, there are some common clustering algorithms that are quick Google search away. Uh, just start with the simplest things. See how your data is. See what kind of baseline you can approach. For example, uh, if your predictions with some of these decent models are like 50%, maybe there is something wrong with your feature engineering or your data, your missing value imputation. Or maybe if your accuracy is maybe 97% with this, maybe then it's time to focus on just improving the models, picking the best models and fine tuning them so that you can push that little bit of extra accuracy. Or maybe if the accuracy is somewhere between 60-70%, maybe your task is to focus on feature engineering, or maybe if it like varies wildly, again, you can figure out what to do. But for starters, just get your model, get your pre-processing, whatever else you're doing done, and then model it with some of these basic algorithms as a starting point. Then you can move to more complex or more optimal algorithms. So fine tune what you have. So these are some of the common ones: logistic regression, linear regression, very good starting points. Decision trees, uh, typically you wouldn't use decision trees by themselves. What you would do is use random forest, and then support vector machines actually in several situations are actually giving very good results, and naive bias, especially if you have text or categorical features. And k-nearest neighbors is particularly helpful, especially if you're clustering. But I mean, for this thing, classification and regression also can be useful depending on the data. And then we look at some advanced models. So boosting algorithms. Boosting algorithms, you will actually see a lot of usage, especially in Kaggle competitions and with tabular data, and even in AutoML tools. These are used a lot. So there are three main boosting models that you will see if you go and look at all these uh, data forums, data competitions, etc. XGBoost, LightGBM, and CatBoost. So if you're interested, do some reading about what they do. But even if not, just keep in mind that these are very good general models, especially for tabular data. So typically, you would want to use this data if you have tabular data and are doing some sort of prediction task, uh, be it classification or regression in your competition, or if you are working or doing something else in that particular task. And finally, ensemble methods. So ensembles are essentially combining multiple models to improve robustness and accuracy. So uh, bagging again is like a way of having multiple parallel models and having like some sort of way to aggregate the outputs of different models. Voting classifier again is, I mean, if you think about it, it's a way to aggregate the predictions of diverse models. So, especially for a binary classification, for example, models will give different predictions, and let's say you have five different models with different predictions. You take the majority vote and say that is the output. Again, stacking is where you have a base model and then you see where the base model is missing, and then you train a meta model based on those outputs, etc. So again, there are common libraries which have implementations for all of these, so you can easily use all of these. So if you're interested, do some reading around this and how they behave. So I will show you some implementations of all of this. Uh, so yeah, I've trained logistic regression, support vector machine, and a simple decision tree. And on this particular data set, you have variance in this course, so you can see how like the different metrics vary with the different models. So all of these are very basic models, but they are very good starting points. As you can see, for the stars, they give a reasonably good accuracy. And especially as a baseline model, these are very helpful if you want to quickly iterate. And let's say you are doing feature engineering, you want to check how good your feature engineering, the features you engineer are, then you want a baseline model to evaluate that. So then maybe you can have these three models which train very quickly, and you can quickly iterate through different features and see how they affect the accuracies, etc. Uh, so yeah, that's for basic ones, and then we'll also take a quick look at boosting. So again, there are Python libraries which provide all of these algorithms, but even if you're using something else like R or Julia or whatever, I'm pretty sure most of them have their implementations. So you can just use those default libraries. And here I've trained all three boosting models, uh, XGBoost, GBM, and CatBoost. And again, you can see now we have marginal improvement of the previous models: 0.875, 0.879, 0.87, and even the statistics are marginally better. So as you can see, these models are better at handling uh, tabular data than the earlier basic models that we looked at. But depending on the data, the improvement might be marginal or might be somewhat more significant. So always see where you should put your efforts into optimizing using models or feature engineering or pre-processing, whatever it is. And also for many of these, I mean, even for these, you can do that. But for these, there are ways to see the feature importance. of different features, how much they contribute to prediction. So here you can, so these are calculated features, but you can actually evaluate, you can actually see what exactly this F32 column is, how it's calculated, and based on that, you can determine the contribution different initial features made for this. And I think these models also provide other tools to determine the impact of different features. So you can look into those things, do a quick Google search, you will come across the libraries for this, and you can see how they work and the different methods you can use to see metrics, feature importance evaluations, etc. And again, I have tried some ensembles here, bagging with decision trees, random forest, voting classifier with some basic these things, and static again stacking classifier with some basic these things. So here for the ensembles, you can see the different accuracies. So for the bagging one with our basic models, there wasn't much of an improvement. But here you can see the stacking one with our basic models, there's some sort of a improvement as opposed to using just the basic models. And of course, if you use better models, this might be more. So we haven't used any of the boosting models here, for example. But depending on what you use with maybe voting or something, you might get better results if you use an ensemble. So make sure to try all these different techniques with your data once you have something working. Once you have your pre-processing, once you have some good feature engineering that you evaluated using the baseline models, make sure to try out all of these and see what works. So these might work, different one particular type of ensemble might be better for your data. So just go through all of that. So next, we come to something I want to mention in practice, which can be very useful these days, AutoML. So what is AutoML? So it's generally the automation of a lot of things that we do in machine learning. So if you look at this work, sorry, you look at this workflow. Based on this, I will probably be doing some sort of data pre-processing. I will clean the data. I will impute missing values. Maybe I will do some basic feature engineering and maybe some sort of that. Then I'll use some basic algorithms, and then I'll be using all these different models or algorithms and ensembles. So all of that combined with fine tuning the models, hyperparameter tuning, uh, and finally evaluating the models and ranking how good different models are. All of these you can do manually, but there are some libraries that do all of these automatically. So AutoML is a reference to those different implementations, those different libraries. So it can be very helpful for you. So I use it first, fast development and iteration. So for example, if you want to check out impacts of feature engineering, specific features. So one thing I want to mention there is, I had this thing on feature engineering, right? Yeah, so depending on different AutoML tool you are using, a lot of them might be using these common techniques to engineer features, but they are not capable of doing any extra annotations or domain specific methodologies that are not based on these sort of common general techniques. So if you're doing feature engineering with those and you're doing AutoML, then you can quickly iterate and just, let the AutoML handle running it through baseline models and showing like the impact of feature engineering, how much importance those features have and how much they impact the accuracies and the metrics. And then you can get very good baseline models and do quick benchmarking. So you just straight away put your data set into an AutoML without doing anything whatsoever, and you can see, okay, you get at least 0.7 accuracy. Then whatever you do by hand, you know, okay, I should be meeting at least this threshold. And again, handles complex code implementations under the hood. So the common feature engineering, aggregation, encoding, whatever steps combined with different models and high parameter tuning, parameter search, whatever it is, all of that is a lot of code to do, a lot of iterations to do. So all of that can be done under the hood, and so very great for prototyping. You can see what works, what doesn't work, what kind of models you want, what kind of features you want. You can quickly iterate and see that. And once you're done with the prototyping using AutoML, maybe you can, for the final stuff, final optimizations, fine tuning, final feature selections, you can just do only that part with custom your actual implementations. And in addition to all of that, if you're not an expert, you don't know much about all these different kind of models, the statistics, the math behind them. But you know what, you have some idea about the domain, you know the business use case, and you have some clever ideas about how to feature engineer based on that. Then maybe you can just adjust your CSV, add those new files, and then use AutoML, and who knows, you might get very good results by using some clever feature engineering and some creative steps, and leaving all of the expert heavy lifting to the AutoML. So of course it has some catches. So there's limited customizability. So how you want the pipeline to go, how the models are made, how different features are calculated, what kind of features are made, noisy features you might not want in particular scenarios. So there's limited customizability. And then if you have a best performing model, maybe if you want to optimize it further, or you want to do some extra steps in the whole process, some sort of customization, you might need to, maybe you run AutoML, you get like a general thing that works best, but then you do a manual implementation of that model and do the final changes to push that final 0.01% accuracy or whatever you want afterwards. And while a lot of AutoML tools come with their own analysis tools like Shapley value calculations, feature important, other feature importance calculations, etc., there may be situations where the interpretability may be limited, especially if there are like some deep learning models which are not very distinct used in the AutoML. So be careful about those things. Depending on your use case, interpretability may be very important or it may not be important. Again, it depends on the data and the business use case. So here are some popular AutoML frameworks. You have H2O, AutoScaler, AutoGluon, Teapot, and I'm not sure if these are free to use, but Google has their own AutoML, and so does Amazon SageMaker. So you can take a look at all of those. I have implemented a couple of them for you. So yeah, I've used H2O with our data set, and I have made H2O frame here, and I run it for 120 seconds with a maximum of 12 models. So basically it'll iterate depending on what comes first, 120 seconds or 12 models. It will keep training as many models and evaluating them and seeing what's better. So ignore this. This something is wrong with my environment, but basically it will just go through different models. So here, for example, it has looked at gradient boosting machine, uh, H2O implementation of a particular model. And here you can see the evaluations of that particular model, how it has performed. We have accuracy under curve. Yeah, so for example, here you can see this value is much better than values I got earlier. And Equal, what's 1 minus this? I think these values are also somewhat better. So this is better than any of the manual ensemble sound boosting models I had made so far. And again, it has next done another GBM model, and again you can see the different metrics it has. So if you go to the documentation, you can see what all of this means, how you can customize this, how what arguments you can pass here, what the metrics are, the impact of different metrics. So it's very helpful. And finally, you can like see a leaderboard. I have not printed the leaderboard here, but you can print the leaderboard, see the different models there are. Uh, Maybe if you want more models, you can increase this to maybe put it to run for like half an hour with 40, 50 models. And then you can pick the best model and do your predictions. And again, I have done one with autoglone. Again, something similar we are doing. If set a time limit, how long it will run for, and it will take its time and run through different models. So here it has run through a bunch of models, 13 models, and you can see the scores that it has for each model. And and you can see like a leaderboard with different these things. Uh, Also know that my earliest course, I think, no, never mind that. Yeah, so you can see here Cat Boost has performed the best here, somewhat similar to what happened with our last time. So this doesn't actually do as much in the way of automatic feature engineering as the H2O library does. So again, depending on the different AutoML you use, you might have different capabilities it can. So in this case, you will have to do any extra feature engineering, significant these things yourself. But again, a lot of these things are covered by it, and you can see feature importances and standard deviations within these things. So take a look at that, and if you're interested, you can take a look at the other libraries too. Go through their documentations. I'm sure these have like a lot of helpful documentation both about how to use the library as well as about the different stuff. There are the different models, the different configurations, the different evaluation functions, the feature importance measures, and why they matter. Finally, we'll take a quick look at model evaluation metrics. So after training a model, we need to know how well is this model performing. So for that, we need some sort of metric. So accuracy is a decent basic metric, but accuracy might not always be the best metric. There are many things a simple accuracy just can't portray. So for that, you have things like F1 score, recall, precision, ROC curves, area under the curve. But you can also come up with your own custom metrics. Maybe, for example, income group prediction. Maybe you can give some weight depending on the age if you want, and make that your custom evaluation metric. Again, especially if there's a business use case where something is important, you can define a mathematical function that gives more importance to that. So I'll just show you some of the common ones implemented again in this code. You can go through this file 6eval, and you can see some basic these things. So precision, recall, F1 score, and macro averages, weighted averages, and ROC UC curve. This in particular, I'll show you later. I'll show you down below. It's a very useful this thing. And from this precision and recall, you can also show confusion metrics, uh, where you have the true positives, false negatives, true negatives, and false positives. So You can see where your model is performing well, where your model is failing with this. And the ROC curve is basically uh, particularly useful for classification where you so most models give like a confidence of like how much it thinks something is positive. So based on the threshold we set for that, you can see how like the true positive rate and the false positive rate varies. And so for that you have the ROC curve, and in this curve what you want is for this one to be at the top left as much as possible. That is, you want the area under this curve to be maximal. Um, so yeah, those are some of the commonly used listings, but you can also define your own custom weighted cost functions. You can take whatever inputs. So you take the Y true, Y prediction, and then you can do whatever else you have with any other importance. Maybe you can make a mapping of some feature columns. So say age, you take in the ages as well for these rows and add a weight to that. So uh, yeah, that's it about evaluation metrics. Metrics matter beyond code, whether you're at the workplace or whether you're in the competition. Uh, you want to choose the right model during experiments based on metrics, but also you want to create like visualizations showing the model's performance using these metrics. If you're making a report or a presentation, you want to add these metrics to show how big the problem you're addressing is, or how much of a difference your models or your predictions make. Uh, and you want to use these metrics to translate from mathematics statistics to the actual business explanations. So if you think about these two last points, they are very important, no matter whether you're on the workplace or competition. So this, since you all are preparing for a competition, I'll tell you, make sure that they are very well explained in reports or presentations, so that because these are the sort of things that will give you marks. Everybody will have some sort of metric, some model, and some accuracy. Maybe it might be marginally better than yours, marginally worse than yours, but this is very important. So for example, here are some real world examples. So e-commerce fraud detection, you want high precision. So uh, you want to avoid blocking good users. So you don't want like a false positives. Uh, so maybe it's okay if like uh, some frauds are like not detected, as long as you don't actually block legitimate users. Or maybe in loan default prediction, they have it the other way around. Uh, you want to catch all the potential defaulters, so that maybe the bank staff or whoever can then manually go through those potential defaulters, as opposed to not catching potential defaulters. So maybe it's okay in this instance if you catch people who are not potential defaulters, because maybe in the real world there will be a second step where humans look at the data and also evaluate them. So maybe that is the case. Or in medical diagnosis, maybe say cancer detection or something, maybe you want a balance of these two, or you want like some sort of custom metric. So depending on that, you can think about the business use case, think about the model you have, the data you have, and try to figure out what you're going to do as a way of evaluating your model. Uh, so with that, I think we have done like a basic covering of things you should focus on when it comes to data modeling in practice. If there are any questions, I think we can take them now. You can speak up and ask, or you can put it in the chat. I'll wait a few minutes.
Yes. Thank you so much, Mr. Sandil Ranasinghe, for that practical, insightful, and engaging session. Your walkthrough of the journey from data exploration to modeling gave us a clear and grounded understanding of what it really takes to build effective data science solutions. We truly appreciate the knowledge and experience you've shared with us today. Just a quick reminder, DataStorm 6.0 has only just begun. We have more exciting webinars and sessions coming your way. So make sure to follow our pages and stay tuned for what's next. Thank you once again for joining with us today. We hope you found today's webinar valuable and we can't wait to see you at the next one. Thank you and have a good night.